Okay, we are almost at the middle of the course, midway. And that's where we'll kind of turn the page from talking about making predictions into generative AI. So this is a transition point. Up until now, we talked about all these different machine learning applications that had one thing in common. In all these cases, we fed data or some content into the model and let it make predictions about the label of that content. In the example of image classification, you give it the image of a dog, and the task of the model is to predict the label, which is dog or cat. And similarly for spam detector, content is the email that comes in, what comes out is a prediction of the label. Same with housing price, so on and so forth. What we're going to talk for the rest of this semester is a different paradigm where you use machine learning to generate data. In predictive AI or discriminative AI, the paradigm is what I just described and what is shown here. Content comes in, label prediction comes out. In generative AI, you input some form of content. It could be noise, it could be a prompt, and the output is the content of interest. Here in this example, you give it a prompt to create an image of a cat, and it will create the image of the cat. If you look at the recipe for machine learning we talked about, where you have this training phase and inference phase. In the training piece, your examples include the input data or the content and their labels, and you feed it into this learning algorithm, build a model that maps the input to the output, the content to the label, and then once it has learned that relationship, you take the model, you plug it into your inference pipeline, where you feed into it the data for which you don't have a label, and it makes a prediction of the label. That's the world we looked at so far, the discriminative AI. In the generative AI domain, you still have that training and inference piece, but they're a little different. In the training piece, instead of having content and their labels, you just have content. You have unstructured content, which means the data doesn't come in tables. And the model learns what the content should look like. And once it's done with that part, and you go into the inference, you provide the model with some kind of content, some noise, some prompt, and it will create the content as the output. If you look at an example of predictive AI, we looked at image classification, where the training piece is feeding a lot of data of the images of cats and dogs along with their labels into this learning algorithm. And then during inference, you give it the data and it comes up with the label, right? Now, in generative AI, what's going to look like is going to be more like this. Say your goal is to generate images of dogs. What you would do is to just collect a whole bunch of dog pictures, feed them into this algorithm, let the model learn what a dog looks like, such that once learned that, you just give it noise to start or something, and it will create the image of a dog. Now, content could have different forms. It could be text, it could be audio, images, video, so on and so forth. And based on that, you could have different type of generative AI, where they can generate different types of content, and also as input, they can take different kinds of content. These types of contents, we call them modalities. So there are different modalities. Audio is a mode, image is another mode. And if a model like the current ChatGPT models can handle multiple kinds of content, like text and image, We will call them multimodal models. Just to guide your thinking here, let's look at different imputations of these models. As you might imagine, you could end up with a whole bunch, and that's part of the reason you hear a lot about AI in the media and in the news, because there are so many different ways that you can create AI products now. Say your input is image. Well, your output could be text, could be image, could be video. If the input is image and the output is text, that could be an example of an application where you feed it the image and it creates a caption for that image. If it's image to image, I can think of the example where you have this old, wrinkly picture, you feed it into this algorithm, and it comes out with a cleaned up color version of that image. Or I've seen some examples, some apps where you give it a picture of a child, it outputs an image of that person when that person is 80 years old, or vice versa. Similarly, you could have input as text, and output as text, output as image, or output as audio, or many other forms. Input as text, output as text. This is chatbots, essentially, GPT models, those chat GPT stuff. You will have coding copilots, that's another example. And all these other applications for translation, summarization, these are all text to text. Text to image is these applications where you type in what image you want and it creates that image for you. What we're going to talk about in this course, the focus is going to be text to text generative AI. And I will talk about why I picked this one category, this type of generative AI for the rest of this course. Well, the models that we use for text to text are called large language models. The phrase language model is hopefully intuitive because text is generally the way we convey language, but it could be other types of text as well. It doesn't have to be human language, like programming languages, or you can get creative with whatever cryptic text you have. And they call it large language models because, as you will see, these generative AI models are generally very large in size, too many the parameters. And example use cases, like I just alluded to, you have chatbots, summarization, coding copilots, applications for writing emails, essays, so on and so forth. But more importantly and more fundamentally, I think these large language models are reasoning engines. And that's bring me to the motivation or the reason why I want to talk about these large language models and not other types of generative AI in this course. Because reasoning engines open up a whole lot of doors that didn't exist before. It's not just about email summarization or chatbots or applications like that, but you can think of these large language models as operating system of a whole lot of other applications. Because up until now, we conceived reasoning to be an attribute of humans only. And now, I believe for the first time, we see these algorithms that are very advanced, even more advanced than humans in reasoning. And I want to give you two examples of what I mean by that, being able to reason and that opening up opportunities. Two examples. One is about AI agents. AI agents are the software programs that you can give them a task, tell them what you want. You don't have to tell them how to do it. And they have enough agency to plan the activities, figure out what needs to be done, use tools to impact the outside world, collect results, iterate, and come back to you with a completed task. One such agent would be a travel agent. Now, the travel agent, like most other AI agents, is going to be a relatively thin software shell in the middle of which there is a large language model as the brain of the agent. And because this large language model has the ability to reason, when you tell the travel agent to schedule a trip to Malaysia in July for 2 people with this budget, it figures out what the steps are it needs to complete. It starts looking on the internet for resources, figures out if you need a visa or not, whether July is a good season, and books the tickets and come back to you or ask questions whenever necessary. And all of that's possible because at the heart of it you have this large language model that is able to think critically and to reason. So you're no longer looking at text-to-text generation like email summarization. You're using a brain for free. That was example number 1. Example number 2 is robotics. Again, at the heart of the robot, you're going to have a large language model to reason and to decide what to do. Up until now, the applications of robots have been very limited by the following. Say I have the task of a charger being plugged into the wall. So if I tell the robot to do it, first of all, I have to figure out how to communicate with the robot so it understands I want the charger to be plugged into the wall. And second of all, it turns out to be an incredibly difficult task to do, because what if there is something already in the wall? What if there are 2 chargers? There are so many. What if the charger is nowhere in the pictures, or it's a different color it's never seen before? And that's why in the outside world you don't find any robots. If you go to a big construction site, you don't find robots running around doing anything, despite all the hype. Now, with large language models, this story is going to be very different. And I really believe the next frontier, the next wave, is going to be robotics for this reason. Now, you have this large language model that is integrated with computer vision, with other types of generative AI, text to speech, speech to text. But at the heart of it, you have this reasoning engine of LLM. So when I say plug the charger into the wall, first of all, I can use human language, and that's great. And the LLM understands what the steps are. First, it has to find a charger, and if the power outlet is used by something else, it understands to come back to you and ask if it's okay to unplug it. All of those things that would have taken years and years to build, now you can do it in a few minutes. And on top of that, you can say, go get the door, see who's knocking on the door, and it will just go ahead and do it, because the reasoning engine inside of it is flexible enough to understand the concept of door, just like a human. So these are some of the reasons why I'm excited about large language models, and that's why we want to focus on this. It's not just text to text, it's the ability to reason and think, right? So let's talk about fundamentally how these large language models works. Let me first show you this typical chatbot interface. If I say, how does LLM work? So how did it come up with all this text? I'm going to give you this high-level intuition about this. So what happens here is, you give it an input to a large language model. Here in the example, say, I am. What I showed you on the chatbot, I said, how does LLM work? That was the input that we call a prompt in the world of large language model. You feed it into the LLM. What LLM does is to predict the most likely word that should follow next. Now, in the next lecture, I will be a little more precise about this, and I will talk about tokens, but for now, let's just assume it's a word, whereas indeed it's actually a subword. But let's say it's a word. So you say, I am. The language model takes that as input and predicts the next most likely word, and that is very. And then takes that very, that output, and plug it or append it to the prompt that I had and creates a new prompt. The new prompt is, I am very. Feed it into the LLM, predict the next word. So at any given time, at every iteration, the LLM is predicting the next one word only. But because it does it many times, it ends up with many paragraphs. And now, when you look at this, it's not just the result of one model run, but many, many model runs to come up with all of this. So this is LLM in action. They call it autoregressive model, where it automatically uses its latest prediction as its history for the next round, and it rides on the tracks as it's building it. So that's the notion of how these LLMs work at very high level. Now we know how LLM works. It's just predicting the next word and then using it, attaching it to the history, and now look at this new history and predict the next word. But that may sound too simple to be effective, too simple to build a reasoning engine. So I want to give you two intuitions on why this could be powerful, beyond that simple fact that it works, and the proof of the pudding is in the eating. When you try it and it works, I guess that's enough of a proof. But let me give you two intuitions. One is, imagine you read a detective story, 300 pages of text, you reach the last page and last paragraph, and that's where they say the culprit turns out to be blank. If you can predict the next word, which is the name of that culprit, that means you understood the story. You're exhibiting intelligence. So there is a lot of information, there's a lot of intelligence in being able to predict the next word. That was the first intuition. The second intuition, again, something I borrow from Andrej Karpathy, is if you take a page of Wikipedia that is heavily used in training these models, by the way, and just read through it, you will find that indeed there is a lot of intelligence in being able to predict the next word. Right? So this is about this album. The name of the album is Title. And as you read through it, for example, just the last piece of it, it says they were dissatisfied with this radio, and they drew influence from now blank. If you can fill the blank, which is retro style 1950s, and another blank, 1960s music, that means you really understood this music genre and the work of this artist, because you were able to tell me that they drew influence from these particular types of music, right? So at this point, you understand what language models are, why they're so important, and how they work at very high level, how they generate text, and finally, why this next word prediction mechanism actually is promising and it works, right? Now let's look at inside of the LLM. So everything we talked about so far was this black box, this little box that I showed as LLM, but what is it like? Well, it is a deep neural net. And in fact, it's a classification model. And let me explain how it could be a classification model. So you have the prompt as input. Say, I am very happy, and it's going to predict the next word, which is to, like to meet you or something. All of this text, after some data processing that we'll talk about, is fed into the input layer of neural net. The neural net has a bunch of hidden layers, but there is this one output layer with a bunch of neurons. It has as many neurons as you have words in your vocabulary. So the size of that output layer is the same as the size of your vocabulary. And the values that are outputted in these neurons represent the probability that that neuron or the word that neuron represents is the next word. in the sequence. Say in our mock example, I said I'm very happy, and what comes out of these neurons, the point 1, that point 2, point 8, point 1, whatever. And the first word in the dictionary could be A, next one could be apple, banana, all the way through, and then at some point you have 2, and then zebra and whatever comes next. And it just so happens that 2 has the highest value output, which means the highest probability of being the next word. So now your LLM, look at the outputs, pick the one with the highest probability. And that becomes your next word. So this is the model at high level. And the reason I said this is a classification model is you have this classification problem where the number of classes equals the number of words in your vocabulary. So you're just trying to predict which of these words or which of these classes is most likely to be the correct class. So this is a neural net then, and it follows everything we have learned about neural nets. Notably, that you could have these language models or these deep neural nets available to the public, called open source, or keep them to yourself, hence proprietary or closed source. If it's open source, you share the model parameters, the weights, along with the code to construct the architecture of the model with the world. If it's proprietary, you keep it to yourself, but you deploy it on your own servers, you make an API available, and other people can just send their prompts to you. You will run it through your model, get a prediction, and then send the prediction back to the user without sharing your model or its model parameters. So that was LLM, how you can get them open source and closed source. Let's see how you can run an LLM. Running an LLM is a relatively trivial task. Again, this slide and the next one is borrowed from Andrej Karpathy's lectures. What you need to run an LLM are 2 files. One of them is a zip file, essentially, that holds all the model parameters, all the numbers, and another file that is the code, the script, that you can ingest the parameters with it and run it. And once you download these 2, you can go off the internet. Here for the Llama 2 70B model, 70B means 70 billion parameters model. You have a parameters files, which has 140 gigabyte of data. It's 140 because each parameters is 2 bytes of data. So 70 billion becomes 140. And a few hundred lines of code. So I'm going to show you now where you can find those parameters and the script. The main repository for these open source models is Hugging Face. So here's the website for Hugging Face. And they have this whole model sections depending on the application or the name. You can search and look for the model you want. This is for Llama 2 70 billion parameters, and in their files and versions you can see a whole bunch of compressed files, and these are your model parameters. You can download them, and the code itself is actually right here. They published their GitHub page, so here is their code for running this model. Everything is here. Let's see how many lines is this. Yeah, almost 500 lines. Right, inference was easy because you're given those model parameters and you can go ahead and use them. Training is very different and very difficult. It's the one that takes a lot of compute resources and a lot of creativity. Essentially, you need a lot of text to use as training data for these large language models. And for Llama 2 70B, the amount of data that was used off of internet was 10 terabytes of text. They used 6,000 GPUs for 12 days that cost about $2 million to rent and run. And the result of all that, you use all this data, feed it into this learning algorithm, use all these GPUs. What comes out are these tuned model parameters, trained model parameters, 70 billion of them. And like I said, that is 140 gigabyte. And you were able to download them off of the Hugging Face, right? And this brings up a new way or interesting way of looking at these large language models. What you're doing essentially, if you look at the left and at the right, is that you're compressing the human knowledge or the world knowledge into 140 gigabyte file. This fits very easily on a memory stick. Actually, bigger models like DeepSeek would also fit on this memory stick. Now, the crazy part here is that we were talking about large language models being essentially a classification model that predict the next class, which is the next word, based on the content that was fed into it, right? Very kind of basic operation, predicting the next word. But now it looks like we created this compression algorithm that took 100 terabyte and compressed it to 140 gigabyte. So that's almost 100 times compression. Now, what I invite you to do is to try to push these language models to their limit. You could go to ChatGPT, you could go to Claude, or try these open source models and see if you can break them, meaning you can prove that they're not perfect. I mentioned and emphasized that these large language models are reasoning engine. They're very intelligent. They're good at logical reasoning tasks. But the fact is they're not perfect. So if you want to play around with open source models, here is a good resource. You go to the playground, and from the playground use chat. And here is kind of like ChatGPT, except that it hosts a whole bunch of open source models. So you can test this Llama 70B, you can try a DeepSeek, so on and so forth. You can pick from any of these and then run your code, see what happens, right? So this is an opportunity for you to test the limits of these language models.